Ladies and gentlemen, hello and welcome. Coming to you once again, not quite live from One Take Studios, where I have an entirely different setup and I don't even know if this is going to work, so I'm praying it does. Today's topic is exponential functions, which I rather enjoy. Our base model for exponential functions is right here. There we go. That's it. F of x equals b to the x. B, if you notice in this case, is the base number, and it's going to be a constant. So within any given problem, it's going to be a single number. Now, what kind of number does make a difference? That base has to be a number that's greater than 0, and it has to be a number that's not equal to 1. If you try to put in a base that's negative, graph it. Let me know what that looks like, because that's quite interesting. If b were to equal 1, that would be just kind of boring, because any exponent that we put on a 1 is just going to be 1 every single time. So to keep it interesting, has to be positive, has to not be 1. All right, great. X is going to be the exponent, and that makes life a little bit interesting. Specifically here, I want to go into identifying the difference between growth and decay. So here we go. This is our alternate model. Please notice it's very, very similar. F of x equals a times b to the x. So we still have the same models. These rules still apply, but we have a multiplier out front. And let's look at how that changes things, shall we? In order to classify this as exponential growth, the a has to be something greater than 0. So again, we want a positive number right here. But b also has to be greater than 1 this time, which makes sense if you think about that. You're multiplying repeatedly by a number bigger than 1. It's going to get bigger, hence the growth. Well, all right, so what's going to make it decay then? What's going to make it smaller? Please note again, the a is still greater than 0. So in both cases, for growth and decay, that multiplier out front, that's going to be a number that's greater than 0. But this time, if I want things to decay, to get smaller, I'm going to multiply by something between 0 and 1. That's going to be a fraction. So like if I keep cutting something in half over and over and over again, it's going to get smaller. It's going to decay. All right, I want to get a good visual for us on this. So we're going to switch over to the graph. And we're graphing pencil and paper here today. First graph is over here on the left. F of x equals 2 to the x. So as you notice, the base here is 2. That fits our qualifications for a base, and x is our exponent. Basic x and y graph set up here. I've got a table going on. Things that we probably know more readily than others. If my exponent is 1, 2 to the 1, 2 to the first power is 2. What if my exponent is 2? Well, 2 squared is 4. What if my exponent is 3? 2 cubed makes 8. All right, so how good are you? What if my exponent is 0? What's 2 to the 0? Well, anything to the 0 power is 1, so that's kind of nice. What if my exponent is -1? 2 to the negative first power. Let's see, negative exponents, that was, oh yes, that was a reciprocal. In other words, this is just 2 to the first power, but we flip it over, so that's going to be 1/2. Okay, not crazy. What about -2? What if we do 2 to the negative second power? Well, that's going to be 2 squared, which is 4. But again, because it's negative, it's the reciprocal. We're flipping it over, so that's going to be 1/4. Take a look at what that gives us then. So at -2, we're at 1/4. Let's say right about there-ish. At -1, we're at 1/2. Yay us. At 0, we're at 1. At 1, we are at 2. At 2, we are at 4, 5, 6, 7, 8. There we go. There we go. What is this graph? Is it a line? Nope. 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 Is it a parabola? Doesn't look like it. In fact, what's going to happen if we keep putting in larger negative numbers, so to speak? What if I put in -3, -4, -5? This is going to keep giving me really, really tiny fractions. So visually, I'm coming close to this x-axis. I'm going to come through my points. And all of a sudden I'm an increase, but I'm not even increasing at a steady pace like we would see with a line. I'm increasing faster. I'm increasing exponentially. Oh, that's where that term comes from. All right. So what is the difference then between that graph and this one? All right, so for this graph, we've got f of x equals 1/2 to the x, 1/2 to the x. All right, the last time was 2 to the x. Well, all right, so difference between growth versus decay. Here we're multiplying by 2, and it's going to get bigger as we go. What would we expect to see here if our base is 1/2? Again, that base is between 0 and 1, so we would expect to see decay for this. Again, let's maybe start with things that we sort of are familiar with. 1/2 to the first power is 1/2. 1/2 to the second power, that's 1/2 times 1/2, otherwise known as 1/4. 0. Anything to the 0 power is 1. What does it look like for negative exponents this time? Let's see here. 1/2 to the negative first power. That's, again, just a reciprocal. So 1/2, the reciprocal of that is 2. Huh, okay, all right. 1/2 to the negative second power. So we're going to square it, but again, we're going to flip it. So that's going to be 4 this time. And then 1/2 to the negative third power. That's going to be an 8, because again, we are going to flip that back over again due to the negative exponent. So this time around at -3, -3, 1, 2, 3, we're at 1, 2, 3, 4, 5, 6, 7, 8. Yay, us. At -2, we're at 4, 1, 2, 3, 4. And -1 is 2. Back here, y-axis is 1. And then at 1, we're at 1/2 this time. And at 2, we're at 1/4 this time. So you should notice a very similar appearance between those two graphs. Some people expect the decay to have dropped below the x-axis, but that's really not the case. We're still talking about positive values, but we're seeing a decline instead of a growth. So very, very similar looking graph coming down through here, hitting our points, turning the paper. There we go, there we go. And again, we're just getting really, really close to that x-axis. So my next question would be then, how close is really, really close? All right. Is there any exponent that I can put on a positive number, either a 2 or a 1/2? Is there any number I can put on there as an exponent that's going to cause it to be a negative number? Well, ladies and gentlemen, that would be problematic, because even if I put a negative exponent on a positive number, it's still going to be a positive number. So if we think about this, there's no exponent that I can possibly put on a 2, or for that matter, that I could possibly put on a 1/2 that's going to allow this to become negative. So this is never going to drop below the x-axis. Will it ever hit the x-axis? Pondering life, pondering life. Anything that I can put on here that's going to cause it to equal 0. You know what? That's not happening either. So on these graphs, the graph is going to get closer and closer and closer to the x-axis for all of eternity. Same thing here, get closer and closer for all of eternity. But you know what? It's not going to get there. What does this mean? That means that we have an asymptote for this graph. Asymptote, in this case, is the x-axis. There we go. I can spell axis. Ta-da! So x-axis. That just means that the end of the graph is forever going to get closer to that line. That's all an asymptote is. I know it sounds like a swear word. It's not a swear word. It's spelled with one S only. Careful there. So with this, yeah, we're just going to keep getting closer to that line for all of eternity. That's an asymptote. So the x-axis is going to work for us there. What does that mean about our domain? For either of these graphs, will it keep going left? Will it keep going right? Keep going left, keep going right. Is there anything that's going to stop it? No. So we're going to say that x is a member of the set of real numbers. There's that double-stemmed R. That's the formal writing. So x such that x is a member of the set of real numbers. There's nothing to stop it, no boundaries. It's going to keep going. But if we look at the y's on the other hand, it's going to be a little bit different here, isn't it? Because it'll keep going up, but will the graph keep going down? Yes and no. It will keep decreasing, but in smaller and smaller and smaller amounts. So it's never going to get to 0, and it's never going to drop below 0. So we're going to say that our y's, or the values are, what do you think? I think greater than 0 makes sense. There we go. Everything greater than 0. We don't want to say greater than or equal to, just greater than, because it's not going to equal. It's going to stay above. It's going to stay positive. All right, so that's what we expect to see for basic graphs there. All right, so there's growth, there's decay, yay us. Let's go back to our other sheet, shall we? So we know a little bit about exponential functions, what they look like, what they graph like. I think we should play a game. You ready? Here's our game. Today's game is called Growth or Decay. Growth or Decay. Ladies and gentlemen, here's our specialist. Woohoo, party zone. There we go, there we go. All right, growth or decay. How much do you know? How much do you think you know? How much are you comfortable with? Here's round 1 of growth or decay. There is our function right there. F of x equals 3 times 4/9 to the x power. Is it growth or decay? Growth or decay, growth or decay. All right, well, let's see here. The A is positive because that's our multiplier. And b is between 0 and 1 at 4/9. But if I multiply this 3 times 4/9, 3 times 4/9, that is something that's bigger than 1. So wouldn't that make this growth? I think it might be growth. What do you think? Wait a minute, that's just silly. Order of operations says that if I have an exponent, I'm going to do that first before I multiply. I can't do the 3 times the 4/9. I have to leave it sitting there, which means this is positive. This is between 0 and 1. Ladies and gentlemen, this is most definitely decay. That is a decay model. How'd you do? Surviving round 1? Yes, no, maybe? Maybe you need a round 2. All right, here's a chance to redeem yourself. Here is round 2 of growth or decay. Growth or decay, ladies and gentlemen, right there. F of x equals 5 times 7 to the negative x. All right, we got this one. This is going to be good. Okay, so the 5. All right. The 7, bigger than 1. This is definitely growth. Definitely growth. We got this, right? You agree with me? This is growth, right? What's that negative doing right there exactly? What is its purpose? Because didn't we say something when we were graphing about negative exponents and being reciprocals? Huh. Interesting. So wouldn't that mean that this is really just 5 times? This would be the reciprocal, so this would be 1/7 to the x power because the negative exponent is a reciprocal, right? Okay, so it's decay, right? Ladies and gentlemen, it is decay. There we go. It is going to be decay. The 7 itself, for starters, that was a number that is greater than 1, which indicates growth, but because the exponent was negative, I tricked you. Woo-hoo, there we go, I got you. Ladies and gentlemen, that is going to be decay. All right, round 3. You ready? Here's round 3. Growth or decay. F of x equals 2 times 4/3 to the x. Growth or decay. It's a fraction. I'm thinking it's going to be decay. What do you think? I mean, we got 2 decays. Let's go for a trend. It's decay, right? What do you think? Did you make the same argument that I did? I'm like, yeah, it's a fraction, but 4/3, seriously? That's 1 1/3. That's bigger than 1. Ladies and gentlemen, this is growth. Did you get that? I bet you did. I bet you figured out that's growth. Way to go. All right, which means we are ready for the final round of growth and decay. Are you ready? F of x equals negative 4/3 times 3 to the x. Ladies and gentlemen, is this growth or decay? Growth or decay, what do you think? This is too easy. Because it's 3. So that's greater than 1, so it's clearly going to be growth, right? Well, but we have a negative, so maybe that's 1/3, right? Because that's just going to be reciprocal, right? So maybe it's decay. I'm sure it's decay. Or if my a value is not greater than 1, maybe it's none of the above. Haha, gotcha. Neither. It is neither growth nor decay because the a value, the multiplier out front, is less than 0. Wah, wah. All right, thus ends our oh-so-exciting game of growth or decay. I have not copyrighted that game, so feel free to play it with your friends. It's going to be good. Okay, so one last thing I want to show you with this today, and that is going to be, where'd it go? Don't peek yet. All right, here we go. Ladies and gentlemen, this is still an exponential function, but it's set up in a way that we use it for application purposes. And so we're going to see if we can figure out what some of these variables mean. This lowercase a that's sitting out front here, that was that same multiplier that we saw over here. Multiplier, there it is, there we go. Same multiplier. What is that? Well, in applications, that is always going to be our starting amount. It's however much we have at the beginning. That right there is the number 1. Not a variable, the number 1. It is always the number 1. Let's see if we can figure out why. R, can you guess? R is the rate. So if we have something that is increasing or decreasing with a rate, that means that we're starting with 100%. Ooh, there's the 1. We're starting with 100% of what we have, and then either we are increasing it by a certain amount or we are decreasing it by a certain amount. Please be careful, the plus or minus here does not indicate that we are going to use both plus and minus. Either we are increasing or we are decreasing. Pick one, okay? Pick one. Okay. All right, T. You got this, right? What's T? T is always time, congratulations. Whether that's years or minutes or whatever, depends on the problem, but it is definitely going to be time, which means what is this? This is a of t. Again, this is a variable, this is function notation, a of t. This is going to be the amount after time has passed. In other words, if we start with this amount, whatever it happens to be for our lowercase a here, after time passes, we will have either more or less, and that's going to be reflected in a of t. So either it increases or decreases depending on the problem. We're going to look at one example briefly, and that example is right here. We have a town with a population of 20,000 people in 2020. The population begins to decrease at a rate of 3% each year. Assuming that this trend continues, predict the year that the population will drop below 17,000. You ready for this? All right, we can do this. Think about what we have here. Think about what we know for our setup. All right, I'm going to go with a of t is equal to, what number has to go here? What is that? You said 20,000, right? That is our 20,000. That's our starting amount of human beings in this town. Okay, parentheses, 1, because it's always a 1. Should I use plus or should I use minus? Again, I'm not using both. Well, it's decreasing. Look at your word clues, decreasing. We are decreasing, so we're gonna do minus and 3%. Do I wanna put a 3 here? No, because if this 1 represents 100%, I wanna make sure that 3% is also in a decimal form. So 0.03, so 20,000 times 1 minus 0.03, close parentheses. And we're looking for, predict the year. We are looking for time information. So we're looking for the time that we end up at 17,000. Where would the 17,000 go in this picture? No, that is the amount after time has passed. That's going to go right here, but I'm not going to plug it in. Why? Because I'm not ready to go to a place that I would use to solve this right now, because that's coming up in the future and I'm not ready to say it yet. In the meantime, what we're going to do is this. We're going to adapt with what we do have, ladies and gentlemen, and that is our graphing calculator, which is going to be our friend for the moment. All right, please notice that I've typed into the equation the 20,000 times 1 minus 0.03 to the x. So I am mimicking right now this equation that we see right here. And graph. What is that? It doesn't look like anything. Why doesn't it look like anything? All right, well, seriously, think about this. What was our starting amount? 20,000. Look at the parameters on this graph. It's nowhere near 20,000, but I do happen to know, because 1 minus 0.03 is something that's less than 1, I would expect to see, if I zoomed way out, a lovely decay model. What I really care about at the moment, I'm looking at Control T here, I'm checking out the table. So I can see, there we go, 0 time has passed, 20,000 people. That's my expectation, that's where I started, and that's where that would be then on the y-axis. I'm looking for when it drops below 17,000. Well, 1 year later, we're at 19,400. Good for us. Keep scrolling. We're still above 17,000. We're still above, oh, right there. In the 6th year past that, we dropped below. Now, when did that happen? Well, if I see here, year 5, 17,174, 16,659, someplace between the 5th and the 6th year. In other words, sometimes during the 5th year, it actually dropped down. So I'm just simply reading my table to get an approximate answer right now. Notice the question that was asked was predict the year. I don't need to get a super specific answer right now. I need to know that, all right, again, in 2020 was, 2020 was 20,000. 1 year later, that's 2021, 2022, 2023, 2024, 2025, and sometime during 2025, it drops below, because by the time we get to 2026, it is down. So ladies and gentlemen, 2025, that is the year that we would predict a fall below 17,000 for our population. All right, for better, for worse, that's it. Let's pray that this video works, and have fun with it. Thanks, bye.